Hi. A few things to get us started. First, please ask lots of questions. I tend to talk faster and faster and faster unless you interrupt me. I think there are a lot of different backgrounds in the room in terms of engineers, computer scientists, some physicists. Is that roughly right? So just, call it out. If we get horribly behind, then I'll eventually drag us along, but I'm very happy to talk to you about this subject, which I sort of deeply love today. So I'm supposed to talk about, standing in front of it, measurement and circuit QED. This is something I've been doing in my life for almost 20 years. And I personally have found it to be very hard to learn from a quantum mechanics or quantum computing textbook what measurement is. So you're going to get a particular slant today. I'm a very practical person. This week when I wasn't preparing this lecture, I've had a series of epic plumbing failures in the laboratory and lots of battles. I'm very much a person comfortable with a wrench. And the other thing I want to say before we get going in this is that quantum measurement, again, I don't know what you've read, I don't know what you've seen. Even as a physicist who kind of lives in this world, there are two almost disjoint camps. For some people, quantum measurement is very paradoxy and Schrödinger's cat, and there's something called the quantum to classical boundary that's a problem, and there's the collapse problem. There are all these paradoxes in this literature. This is not that talk. Measurement is a very practical thing. We do it every single day. I would say it's an engineering task, except I have zero training in engineering, so if I'm doing good engineering, it's probably on accident. But really, today's talk is no paradoxes. It's a thing that we do every day in the laboratory, and then if you want to be in the business of building a quantum computer, you will also have to take on. To start us from sort of a very specific, still somewhat abstract point, whenever I think qubit, I think the block sphere. I don't know, again, have you seen the block sphere this week? Right? So this is a NMR technique for classical ensembles of spins that's been adapted in the literature to qubits. Basically, you have a qubit, it has two levels. There's two confusing notations, G, E, and then F, 0, 1, and 2. I'm sorry, I will mix these shamelessly. Some the literature uses them interchangeably enough that I often will go back and forth if I'm not careful in this talk. We will label the cardinal states of our qubit as 0 and 1. If I were to draw an imaginary barber pole between the north pole and the south pole of the block sphere, everything along that line, that's the physics of classical coin flips. Okay? So any sort of random or pseudo-random classical process where sometimes you get heads, sometimes you get tails, this part of the block sphere right here is exactly that. The pieces that make it interesting in quantum are states along the equator, where I have the states plus x plus y, minus x minus y, right? Anytime I can write a good old-fashioned state, here's the canonical state of a qubit, right? Some superposition of G and E. Anything where I can write a ket is actually a vector pointing to the surface of the block sphere. Okay? So in basic quantum mechanics, like Schrödinger mechanics, only deal with perfect states. It's actually really a problem in a measurement lecture because measurement is deeply pointless when you already know the answer. I think we can agree, right? So I'm going to flip back and forth in this lecture between the physics of pure systems, where it's going to be a ket that I write. Anytime I just write an unvarnished ket, that's a pure state, a fictitious theorist state, as we would call it. And then, for instance, I will sometimes then switch between that and density matrices. This is the more complete, the more correct, the more practical view of quantum systems. So a density matrix describes not just the skin of the sphere, but the entire interior of the sphere. So imagine I drew a vector, for instance, along the same line as before, but it doesn't make it all the way to the surface. What that represents is a real state in real life, where I know mostly it points this direction, but not perfectly. Or you might say, like, the qubit wasn't perfectly cold when I started, so there's some thermal noise in there, right? So any kind of state where I want to describe pure or impure states together, I'm going to need to use a density matrix. And so in today's talk, you'll see me flipping back and forth. A lot of times the math is easier if we do pure states, but then there's nothing fun to measure. And so we're going to do it. Again, if I screw up, if I'm unclear about this, just let me know and stop me. And so a common example of what this would be is something like this. Let's imagine I have a density matrix where 52% of the time I prepare E. And then by definition, 48% of the time I prepare G. So then I will write this density matrix as 0.52 EE plus 0.48 GG. Just looking at this, does this look like an almost pure state to you folks? To an impure state to you guys? What do you think? Close to pure or close to impure? Close to pure. Yeah, it's actually kind of the opposite, because what's missing that would make it a pure state? A very similar pure state would be like the state plus x. So if I write psi equals plus x, right, that is 1 over root 2g plus 1 over root 2e. And what you guys are latching onto is that when I measure probabilities here, it's like 50-50. That's exactly correct. But when I write this as a, silly notation, right? That's a ket, that's a bra. This is a ket bra. When I write it as a density matrix, rho is just this state. I'm going to get 1/2 GG plus 1/2 EE. That's what I kind of set it up to look like. But very differently than this one, there's some terms that are missing here. And this is what are called the coherences. The fact that it is not just a classical mixture, the fact that it lies on the surface and not very close to the center of the Bloch sphere, is all about these coherences. Confusingly today, if we measure Z, the Z measurement can't tell the difference. It doesn't know about these coherences. But I just want to set this up. And again, I think this conflict between what's pure, what's impure, what do we know, what do we don't know, is really central to sort of measurement stuff that I want to do. Okay? Because it is a little bit tricky to tell automatically whether the state is pure or not, there are kind of a couple different ways that, again, I'm just like setting up some math. This is, I actually found it pretty good. When I think about this stuff, where I tend to go to check it is like the first 2 chapters of Nielsen and Chuang. So if you want to go, you frowned because I say Nielsen and Chuang? Huh? Yeah, it's not a friendly book. But still the best reference I have to this kind of stuff. So if you have some density matrix, it's a little hard to tell automatically whether it is pure. To be legal, to be like realistic, it has to always give an answer. That just says that the trace of rho is 1. That basically these probabilities where the kets match and the bras match have to add up to 1. Whether it's pure, is whether the trace of rho squared equals to 1. So you can think of this as like a proxy for how pure am I. Trace of rho squared equals 1 is a pure state. That's one where I can write the ket. Where this number is rather small, and how small it can get depends on the dimension of the system. For qubits, this can go between 0.5 and 1. When it gets smaller, it's a less pure state. You can directly think of it as a Bloch vector that is shrinking towards the most confused place on the Bloch sphere. Actually, it's very natural to think like, if I lose my energy, that's bad, right? It's true, it destroys your qubit. But if you lose all your energy, you end up on the surface of the Bloch sphere again. You know exactly where you are. That's a pure state. The most confused place in the Bloch sphere is right here in the middle. It is a quantum system that is so scrambled that it looks completely the same, no matter how you measured it, as a classical flipped coin. Okay? Okay. I'm going to pause there for questions. Yeah.
So, G times E, what would that look like?
Like this ket bra?
Yes.
what does it look like? So if I take the block vector here and I write it as like a vector, I can say it's like x naught, y naught, z naught, right? So this is like, I'm just treating this like a normal Cartesian space. If I were to write the density matrix, so rho, as a matrix, I would find that, I hope I don't screw this up. Is it over 2? If I were to write this as a matrix, I would find that the z component, because this is all written in the z basis, is this diagonal element here, where these probabilities are between 0 and 1. The coherences are exactly this thing that exists along the equator, the x and y coordinates. And if I were to write this matrix and like label each piece, this element here is the prefactor for this, GG. This element here is EE. And these coherence ones here are these two guys. These two off-diagonal components right here. So these coherences, what they mean physically is, do I have some x and y quantum superposition or not? If I just have a boring state like 1, that is both a pure state but has no coherence. Somewhere along the equator, whether or not I have coherence is like how much horizontal displacement I have towards the surface of the Bloch sphere. Does that help?
Yeah.
Okay. Other questions?
That should be on equatorial plane.
On the equatorial plane, yeah. And this is, again, where I've used the z-axis. Sometimes people redefine the axis, like x is the north-south axis of your Bloch sphere. All this stuff just rotates. Okay. The reason I wanted to take us immediately into this more irksome land of density matrices, again, is because measurement is only really fun and interesting if you don't know where you are. However, the business of the qubit designer is to make qubits that live a long time. Yeah? So, in reality, what do we spend our time doing in the laboratory? For instance, this might be a transmon qubit. You may have heard some about those, especially from Steve Gervin. The business of the experimenter is to basically build a box around this qubit to seal it off from the environment. Because the qubit is going to tend to have energy relaxation, so that will irreversibly decay. So that's gamma 1 typically in the language of NMR. This is T1, gamma 1. This is loss of energy. This is the thing we want to prevent. We don't want this qubit to lose its energy to the outside world. We can also have dephasing. And dephasing is exactly the thing that will take a pure state, for instance, x on the equator, and scramble it to that same impure mixture state. Okay, so when we talk about circuit QED in the second half of this course, we have to build all our measurement machinery in such a way that still protects the qubit, that doesn't either allow energy to escape, so that will take the Bloch sphere from north to south, kind of collapse you onto the south pole, or that will dephase you, and that will basically like take this ball and kind of squish it into a, I don't know, not like kind of a football, a narrower and narrower football, right? As it destroys these lateral coherences. Okay, so of course, the first business of a good qubit designer is to put this sealed system around the box. And honestly, if you read a lot of the theory of quantum mechanics, what they implicitly do is just leave it there. They have a sealed system. They don't worry about how information gets in and out. It's deeply unhelpful for a person who has to build the machine. So obviously, what we have to do is open portals into this box, ways to get stuff in and stuff out. And how well a job we do that is going to be how well our gates and how well our measurement work, right? All the basic machinery of all this error correction stuff you've been seeing. And I just want to describe sort of two different examples, again, as way of orientation. Typically, my qubit drives in my system are like microwave pulses. If it was an atomic qubit, like a neutral atom or an ion trap, it would often be like a laser, again, some kind of coherent pulse. If I have opened this portal in such a way that I can put in a pulse of light, it interacts with my qubit in such a way that it changes its state. And that pulse, when it comes back, any observer, this is my bad handwriting for an eyeball. If any observer, you, someone else, you give them any machinery they want. If nobody who has a look at that outgoing beam of light can tell what's going on with the qubit, that is a gate. That is what is called unitary evolution for the system. That is something where if I prepare the qubit in the initial state psi I, it will just unitarily evolve. Sorry. To psi f, the kind of interaction, the kind of manipulation I'm building with this pulse of light will be described by some particular unitary operation. Okay? I think it's pretty confusing when like a specialist in superconducting qubits starts talking to you about all the various drives they're applying to the system. Because in all of the cases, they're going to impinge some microwave pulse on their qubit typically. You, as the observer of the lecture, or of the qubit, if you have to tell the difference between whether it's a gate or a measurement, just think, from this outgoing beam of light, which has interacted with the qubit, can I learn something? If I can learn nothing, it's a gate. If I learn a lot, probably call it a measurement. There are weird halfway ones where it's neither really a gate nor a measurement. Honestly, we've written some nice papers on that, but that's not part of like the engineering approach to quantum computing. You're going to really want something to really give you very little information or a whole lot. The other reason I'm focusing on this is because unitary operations, in terms of this block vector, again, I've always got in my head this like balloon of a block sphere. It's always got some vector pointing in it. A unitary does not stretch or shrink the block sphere. So it's very unlike the dephasing or decoherence I showed you. Those tend to take a nicely inflated block sphere where I have good living qubit states and squish them to dead ones, right? Unitaries are like you grab the block sphere by 2 points. Those are going to be the states with don't change under the unitary, and then you rotate it by some set amount. I often have a beach ball. I'm sorry I didn't bring it today. So you just have to imagine I'm holding a beach ball. Unitaries just spin, right? And in terms of, is my state pure? Have I done a good thing or a bad thing to the information I know about my state? They do not change it. So I can't show you information, loss or gain in a pure state. That's pure, very boring. If I just rewrite it in terms of some impure state, imagine a vector that's inside the block sphere. Rho f is going to be u, rho I, u dagger. Basically, the operator unitary u, same one as above, goes on both sides because this is like a ket bra. It has this particular shape, so I have to manipulate both sides of it to do the transformation. I told you before that the trace was how pure it is, trace of rho squared. So if I want to do rho f squared, then I'm just going to write u rho I, u dagger, u rho I, u dagger. U dagger u is defined to be identity for a unitary. And the trace has this nice property that it's cyclic. So I can rewrite this as equal to trace of rho I squared u dagger u by basically taking this one from the start and putting it at the end. That's again identity. And what I get is that trace of rho f squared is equal to trace of rho I squared. Unitary operations cannot make the qubit worse. They can't make it better. Okay? So whenever you saw error correction in the last 2 days, you will notice that there are always sort of a couple different pieces, and one of them was always a measurement. Because if you like, noise in your quantum computer is always trying to kill your state. It's always trying to make it less pure. Unitaries are part of the solution, but they can't be the full part because they'll just take this giant, don't get me in trouble with this, but in my small-minded way, how do I think about a quantum state of a really big system? It's like a really big beach ball with awful lots of dimensions. And the unitary is still turning the beach ball. It's still just rotating states between bases. Noise is always trying to crush it, right? And so then I have to have something that can push back. And that something here is going to be measurement. Okay? So now, I'm going to take this same idea that we've just gone through. I'm still going to take some idea that I'm going to send something flying into the box. In today's lecture, like I really only consider 2 examples. It's either a qubit, a flying qubit. I'll show you like a silly picture of one in a little bit. Or it is a pulse of light, which is also basically a qubit. Okay? And then instead of setting it up so that nobody learns anything by capturing this pulse of light after it's interacted with the system, in fact, the entire design of what I send in and how it interacts with the qubit is going to be so that it does carry away information. And so in the pulse diagrams of the last couple days, you've seen lots of blocks that look like this. There's either some state or some density matrix coming in. There's some unitary transformation that gives you a new state or a new density matrix going out. The kind of quantum measurement that we're going to talk about today is a similar thing. There's some state going in or some density matrix going in. But now there are going to be two things to consider. One is, what happened to my qubit? And so that's going to be represented by some final state or final density matrix. And then this double bar here means like classical information. I'm going to consume whatever this qubit is I sent here, the secondary qubit. What it teaches me is going to become a classical bit of information I have in my hands. In superconducting qubits, we would say at room temperature, outside the machine. And I'm going to use this thing called the outcome to describe some measurement in some operation that happened on the qubit's quantum state. But now, unlike the unitary, which is just you do a thing and it just does it. Here, you're going to have to know the outcome of the measurement in order to figure out what's going on. Okay, so let me pause again there for questions. Yeah. So yeah, exactly. Like so there's two quantum systems, and for the rest of the day, there's always going to be two. The thing I'm trying to measure, I often call it the stationary qubit, and then this like sacrificial quantum state that I'm sending in. It, as I'll show you in just a couple slides, is going to die horribly. As it dies, it's going to give me some kind of information about it, which I then use to track back to the primary qubit, the thing I was trying to measure.
So we are measuring either the laser or...
Yeah, if we send, yeah, okay, but let me just skip ahead to that. So I'm not very good at drawing, but I have historically these nice set of, and I know this is a little simplistic using, but I come back to these kind of pictures in my mind all the time. Here is the qubit in the box, the protected one. It's purple because ground is blue and excited is red. This is some superposition, okay? Like some pure state across the equator. The pulse is a flying qubit. You see its little Superman cape, right? For today, this is not going to be classical, and this is not going to be allowed to be impure. This is a perfectly pure qubit, just like I want this one to be, just to simplify the math so we don't drive ourselves nuts, okay? Imagine he's prepared in some well-known initial state. Again, I'll just write all this math for you on the board in a few minutes. But in your head, two qubits, one of which I'm going to actually get the information from and kill, one of which I'm going to protect. And so the way I build a measurement of this purple guy is to send in this well-prepared initial state. While it's kind of inside the box with the qubit, they're going to have some coherent interaction. A unitary like gate, basically, is going to happen between these two. They're going to become entangled. That's a key piece here. Because Bell pairs have this really nice feature that what happens to one has influences on the other. That's how I'm going to like spread the information across the two. So like if this one's in G, that one's in G. This one's in E, that one's in E. They're in the Bell state. If I just go back a slide, you can really think of them as like a heterogeneous Bell pair after this interaction. You've got the stationary qubit, you've got the flying qubit. I prepared them in a Bell state by this coherent interaction. Then what happens is the flying qubit, after it's been entangled with the primary qubit, goes into this like wood chipper Fargo looking thing here, where it will be destroyed irrevocably. And what's left is some meter, some answer that I, the observer, can see. The flying qubit, it's dead. But the fact that this says G tells me that that qubit has been left in G. So there's three pieces. Prepare the initial state, pick your poison of what kind of flying qubit you're going to do. Build the interaction with the qubit you want to measure, and then consume it. Yeah?
So if qubits keep getting destroyed, does that mean we have to keep putting in more qubits?
Yeah. That's in fact, for instance, in superconducting circuits, while we really like to use pulses of light because we just make them in a generator on the bench.
Okay.
I actually have an example for you. Like this is this is not an abstract experiment. My little cartoon makes it. See, this is one of the first quantum measurements that we know of. In this case, the qubits. There was not two kinds. They're just a flying qubit only. They are silver atoms. They were being deflected by some field gradient. And the fact that they only went here and only went there was showing that the spin of these silver atoms was quantized, sort of. There's a really nice article you can read, another one in APS Today. So really, like, this is a physical meter. There's nothing abstract about it. Imagine that you had good eyes. You would send one silver atom. You would see it landed kind of on the left half of the screen, on the right half of the screen. You would then know what final state the measurement, which is basically the screen, had projected your qubit onto. It is, however, not a coherent object that's still available to you. It went from this nice flying thing to it's stuck to the screen and destroyed. To your question, so I guess this is, this already got its Nobel. This is what's called cavity QED. So this is a paper by Serge Haroche, who invented some of this stuff. This is, again, an atom. They're going to use light to prepare it in a very puffy state, what's called a Rydberg atom. This is also used in neutral atom quantum computers these days. And the measurement apparatus, after it flies through, is going to basically selectively ionize it. Say if it's in state 0, ionize it, and it'll hit a detector, and I'll get a click of charge. If it's in state 1, don't ionize it, I won't get the click. In both cases, the atom is destroyed. It either hit the far wall or it hit your detector. Okay? So the primary system, the flying qubit, the measurement part, is getting destroyed. I kind of need that part to get me something to room temperature to the macroscopic classical world where I can make a decision based on it. Because it tends to destroy things, I'm always going to use this two-step process. So for instance, here in Haroche's experiment, there was a microwave cavity in the middle. That's protected. Nothing bad happens to it. He just sends the atoms from left to right. They measure the cavity. This one he will look at the evolution of. He's constantly, yes, has an oven that will eventually run out of whatever these atoms are if he doesn't refill it. You don't like using physical atoms? Well, that's fine. I don't really either. When you want to think about detecting photons or pulses of microwave or optical light, here it's basically some variation of a camera, right? When I was younger, there were these articles that said that like a human eye, properly prepared, could read out a single photon. So when you think about the observing apparatus, you literally could like have some, qubit, you're measuring it, you are the observer, do you see a sparkle in your eye or not? This is actually a recent paper saying like human eyes are decent quantum detectors. They're not perfect. In reality, it's always some kind of camera who has been optimized to the wavelength of light, right? Whether it's infrared or UV or optical you want to use. Here's a really pretty example. This thing is called a super Kamiokanda. It detects neutrons. They're the primary thing it wants to know. By seeing the light that they give off, here's a whole bunch of detectors ringing it. This is also kind of how I think about like the environment surrounding my quantum computer. It's just a giant pile of eyes all trying to observe it and destroy it if I don't protect it with that box. So that's a lengthy answer to your question, but does it help? Cool. The reason we don't just measure the qubit directly, the reason I don't take the transmon out of my machine and flip it into my detector is because now it's not available for further experimentation, right? Like that kind of direct quantum measurement where I look directly at the quantum system that I also was using in the quantum computer tends to like destroy it horribly in the measurement apparatus, the wood chipper. So we really want measurements that look like this, where I can take some state, get an outcome, it projects me onto a new state. And this is the kind that I'm going to specialize in today. Okay? So if I go back to the board and to the math, I have to sort of set up one more sort of distinction, which is what I would call a single shot measurement versus an ensemble measurement. Again, if you open your textbook, or sometimes you even look in one of these quantum computing texts, they don't show you this kind of complicated machinery. They say, imagine I've got some observable O. If I measure it, does someone want to say what you found in the textbook about, yeah?
They talk extensively about the von Neumann measurement model, which is essentially an abstraction of what you're doing.
In a nice book. in Griffiths, they say that measuring an observable O is this thing. It's like some expectation value. And so that's saying, like, I take some initial state, and I just mathematically do this, and I will get, some continuous answer between 0 and 1. Yeah? Or minus 1 and 1, depending on how you set it up. The tricky thing here is that's not wrong, but that's a result of taking my machinery, preparing initial state, doing this measurement apparatus, getting the outcome infinity times. Okay? And it is an ensemble property. So whenever we talk about measurements in your mind, you really have to keep ensembles, which are going to be like, do the same experiment over and over and over and over again, get some big string of numbers, which we'll come back to. Versus do one quantum experiment, and while the system is still live, do something else. That's the one that looks much more like error correction. Okay? So don't think this. Okay, Steve has gone into his office. Good. I already got Nathan in the back. Steve in the back would be cheating. Okay. I want to just explore this because it's not wrong. It's just not. It's just not the full story. Like, this is still a thing that you can do. Yeah. Yeah. Yes. That's right.
But how do you get the probability distribution?
You don't. Yeah, that's exactly the for the next 30 minutes, that's exactly the distinction we need to tease apart. In your head, you can either do infinity measurements over and over again. That tends to be a thing we call tomography. Or you can do one shot and make a decision, which is typically what we would call feedback or error correction. Or state preparation. We use it all the time. But the two properties are nothing, they have almost nothing to do. They come from the same underlying math, but their utility is vastly different. Okay, so that's not what I have shown you yet, but where I'm going. You're just in time. This kind of math, just to work it out, if I take again my usual canonical pure state, alpha g plus beta e, and let's say the operator is x, and I then just do a little bit of matrix mechanics. O is going to be this ket times the x operator, which is just 0, 1, 1, 0. Alpha beta is psi, so this is psi, and this is psi star. I work this out. I make it alpha star beta plus beta star alpha. Okay? Alpha and beta are continuous quantities. This is also a continuous quantity. And then, to get a particular answer, if I prepare the state, for instance, psi I equals little plus x, by which I mean 1 over root 2, 1 over root 2. Then when I plug this in, I will get that the expectation value of x is plus 1. Just exactly what I expect. I prepare the state along x. My ensemble of measurements will always give me plus x. And I get this value, on average, plus 1. I can similarly prepare minus x. Let me go higher on the board here so people can see it. Minus x is the vector 1 over root 2 minus 1 over root 2. And that's going to give me expectation of the x operator minus 1. And then, of course, if I prepare some other state like plus z, which is just 1, 0, I'm going to get that the expectation of x is 0, right? So what I can think of as this expectation value is doing is it's just reading out the component of my block vector along the x direction. And this is exactly what I will get, as I show you here, if I prepare the system a whole bunch of times, and I just count how many times it gives me 0 as the outcome and how many times it gives me 1 as the outcome. Okay? Then the probability I will infer is directly linked to the expectation value of the measurement. The picture that I want to emphasize today, however, is of that one single shot. So the little machine that I'm going to build, and again, it's like the circuits you've been seeing, but vastly simpler, I expect, is just that I have my qubit and I have my flying qubit, the pulse or atom or whatever have you that I'm going to use to read this thing out. I prepare the qubit in psi I. I prepare the flying qubit in some particular initial state. The choice of initial state, the choice of interaction that I build, that will tell me what kind of measurement operator I build. I'm going to build like a Z measurement operator here, so I'll just prepare it in ground. I showed you that step 2 is a coherent interaction. I'm going to model that as a C0 gate between the two while they're next to each other. And then it flies off into the meter. And the meter in this case will give me the outcome 0 and 1. OK? The state at the initial point before they've interacted is just a tensor product of psi I tensor 0. I can write this as alpha g comma 0. So I'm going to use this first position for the qubit, the second position for the flying qubit, plus alpha e 0. The C0 gate will basically, the way I've set it up now, is to flip the second bit if the first bit's in E. That's going to transition this after the measurement to an entangled state, alpha G0 plus beta E1. I'm not going to try to do the math of the process where it flies out and hits the screen. That's that quantum to classical transition that I don't want to get us all hung up in. However, what I'll point out to you that in this Bell state, what happens is if I can project the second one, then it'll project the first one. OK? And so now what I want to do is to take this whole thing, kind of ignore the secondary qubit. I assume I have that machinery up. I can do it on demand. And just go back to this picture of a box. I send in some density matrix. I do some particular measurement operator indexed by outcome M. And then given M, I want to know what's rho f. OK? The math that allows me to do this kind of simplistic measurement, is what's called a projector set of measurements. The M sub m's, if I go, let me here, get myself some space. The M sub m's that, for instance, for a Z measurement describe what's going on are just projectors. So for instance, I can have an M0. That is like the outcome where this meter reads 0. And this is just called a projector. OK? It's kind of a simple and brutal thing. Whatever's on the right, your new state, when you act it, is 0. Projects you onto 0. If I get outcome 1 from my meter, it projects me onto 1. OK? I call this a Z measurement operator. It looks like Z because when I think about operator Z, it is a set of eigenstates like plus Z minus Z, or if you like 0 and 1 in my notation, with eigenvalues m equals plus 1 and m equals minus 1. I turn these states into projectors. It uniquely describes this operator and this measurement operation. So this is not by itself doing the unitary plus Z. It is a set of projectors whose eigenstates are exactly the same eigenstates as the unitary. Nathan, you're frowning. OK. So that's, I don't know if that's good or bad in this case.
I guess one historical point that's interesting is that this is exactly the same scheme that von Neumann proposed for conceptualizing measurement like back in the 30s as well. And also, this is the basis behind the linear combination of unitaries method for implementing projectors. So there's a lot of ties to other stuff.
Yeah, I think historically the computer scientists knew exactly what they're about, but those of us who trained as physicists come from a very different place. If you look at, OK, sidebar, as long as we're going there. I have major beef with most physics quantum textbooks because they're heavily influenced to teach like the high energy physics perspective of quantum when it was like very hot, which is like the 50s and the 60s, kind of the peak of like big detector physics, you'll notice that at the back there's always like several chapters on scattering theory. It has nothing to do with me. I am never going to scatter a thing off another thing on purpose. Nathan is correctly saying that the computer scientists knew how a computer worked, and therefore like they just added the quantum and they were into the quantum computing business, right? The physics had a very different perspective, and that's why I was saying to you earlier that there are a lot of paradoxes, a lot of stuff in textbooks that I find perfectly unhelpful when learning how to do quantum measurements, because from this sort of physics perspective, the assumptions that they're typically based on are that quantum systems are really hard to control and that they're really hard to measure, and so that you're always going to live on the margins. You will never do a measurement that's just as simple as this, where you just do it and you get an outcome and you're ready to go. And so when that's your perspective, you write this ensemble measurement and you're just done. Quantum computing sort of dared to dream long before physicists could do it what such a machine would be. And so now you have weird people like me who are stuck in the middle, right? Who are trained as physicists, but build this machinery. And honestly, like until we sort of have a new generation of textbooks that are friendlier than Nielsen and Chuang, I hope Ike doesn't, hi Ike. This goes on the internet, right? Yes. That are friendlier than Nielsen and Chuang, let's say, but more hybrid than a pure physics or pure CS textbook, it's gonna seem mysterious. Is that, okay, Nathan's frown is gone. So now we have to do the obligatory Einstein quote, because I am trained as a physicist. So this kind of business, you prepare a state and you like roll a dice to get the outcome, is one of the things that made Einstein unhappy famously. He like doesn't like that God plays dice with the universe. I would point out, if you have control of your quantum system, if you prepared the state well and you did unitary operations on it, measurement is pointless. You already knew the answer. There is no uncertainty. You felt like rolling a dice, and so you went to Vegas and you did it. You didn't have to, right? So I really want to come to you. Most of the quantum mechanics that's easy to write are pure states. Measurement looks funny for pure states. It is a deeply pointless thing to do because you already know the answer. Yes? There is, because you did a stupid thing. You prepared a state that pointed here, and you say, does it point along here? The answer is no, but you knew that. You didn't need to do the experiment at all. You didn't need the measurement outcome. Did you?
Well, but you know, that's the premise of quantum computing.
Even in quantum computing, it's only worthwhile to do the measurement if you can't follow the quantum computer by hand, or you're fighting errors, and therefore there is uncertainty. In both cases, you can't write the state. Yeah? But the toy examples I'm doing today are never so big that that's true. And I really think this, in my mind, is one of the key places where I still get hung up with measurement. If you know the state, it is pointless to measure, and in fact, a deeply wasteful thing to do. If you don't know the state, measurement is magical. And that's the example that I'm going to pick right now. Let's imagine your qubit has had a rough day. It has been fully scrambled, okay? So its density matrix, rho, is GG plus EE over 2. This is not a pure state. This is, in fact, the most confused I can be about what's going on with the qubit. If I run the measurement operation, then I have to give you two pieces, both the probability of getting a particular answer and what happens to the state of my qubit if I do that. The new final state of the qubit, indexed by the answer m, is just m sub m rho m sub m Dagger over the trace of this whole thing to respect the norm. Okay? So I'm going to take these set of projectors. I'm going to run the experiment, get an answer for that one shot, then apply that operation to the system and say, what's the new state? The probability of that, right, that I have to then figure out how often is going to happen, is PM is just the trace of m sub m rho m sub m Dagger. Okay. Both Nathan and Alex have gone back to their email, so good. I think I'm out of trouble. In this case, now, Unitaries don't change the state of the system, the purity of the system. Measurement does, okay? The magic of measurement in this case is now, when I did it, I was a fully scrambled qubit. I don't know which outcome is going to happen. I didn't have any previous information to even predict what's going to happen. But now, afterwards, I'm always going to get a pure state. If I get the outcome 0, little m is 0. Yeah, I need to space back again. Which will happen with p sub m equals a half. Then the final state of the system is going to be 0, 0, acting on this density matrix. Tell you what, I'm going to write these as matrices to save myself a little bit of heartache. This is the operator 0, 0 written as a matrix. Here's my initial state, which was scrambled. Here's the same projector again. It's Hermitian, so when you dagger it, you get the same thing, divided by a half, which is this thing I've sort of calculated offline. And then I'll get that the final state of the system, when you get answer 0, is the pure state 0, 0, when I multiply these things all out. Oh, my bad. Thanks. Yeah?
So could you say again, what is the trace in the denominator of the calculation of rho after?
It's just this thing, and I took the trace.
So, like, in the formula part that you're standing in front of now?
It's the trace of the.
Okay.
It's the trace of the numerator.
That's what I thought. But,
Yeah. It's the it's this. It's that same PM thing. Okay? And so now this in like one slide is why I'm excited to be doing quantum measurement all of the time and like why it's such an amazing tool in the laboratory. I took a scrambled state. I didn't know where I was, so I did have to roll a dice. But kind of I win every single time. Because if I get the outcome 0, I'm in the state 0. So now I wrote it down here. Measurement tells us very little about the past. It's actually very hard, in a second we'll talk about doing tomography. If I really didn't know the initial state, to back it out from a series of measurements is very challenging. But moving forward, that one shot of measurement gives me a perfectly deterministic state to then move forward from in my computation. I measure it, I get 0. Moving forward, I'm in that pure state. I do whatever else I wanted to do with this qubit. This is actually in my laboratory how we reset qubits. Because see, there's a little bit of a problem here. When I was a young student, qubits lived 100 nanoseconds. If I wait 10 T1s, that's a microsecond. So I can do one experiment, a microsecond. The qubit resets itself just by waiting, right? So now after 2 decades of work, we've made qubits live a millisecond. 10 milliseconds is a long time compared to a microsecond. So in fact, a good qubit takes forever to reset. But if you've built this machinery of good quantum measurement, you don't care. You deliberately scramble the qubit, and you measure it. Because you'll notice here that the other half of the time, I'll get the 1 state, and I'll also know that. If my machinery is fast enough to make a decision, to tell the computer what next pulse to play, let's imagine I want to prepare the state 1. I'll just measure the system. If I get 0, I'll do a pi pulse to flip it. If I get 1, I'll just leave it alone. But in both cases, I've now prepared the state. Or I can be lazier. If I get 1, throw the state away, only keep the ones where I get 0. It only works half the time, but half of the data at 1 microsecond is vastly better than all of the data at 10 milliseconds. And so this is why my whole rant, why I get worked up about the consequences of measurements for pure states. This is basically all we're going to use measurement for over and over and over again in our error correction, is that we're going to have some indeterminate state. Something bad is going to happen to the purity of our system, and we're just going to use measurement to dig our way out of that hole. This is, if you like, the magic of quantum measurement in one sort of board. Yeah?
So basically you're never measuring, you're just resetting and then putting it where you want it to be.
I never let it reset on its own.
Okay.
I measure it, and therefore I always put it where I want it to be. So instead of using this measurement at the end of the experiment, I use it there also, but I use it at the beginning to get going. This also is very handy if your qubit has a finite temperature. It won't relax to the ground state. But if you have good measurement machinery but a hot qubit, you don't care. So fluxonium, for instance, is a qubit that does not relax to the ground state because typically its frequency is too low compared to the temperature of the fridge. But if you have fluxonium with good measurement, you'll prepare it via measurement. Yeah, and so you can imagine that your quantum computer has to have good measurement, but it doesn't have to relax to the ground state. It's nice if it does, but actually if it's a good qubit, it's so irksome. Like some of these atomic systems take seconds to relax. You don't really want to wait seconds, right? Okay, other questions? Okay, so now this is sort of cheating. To do this math, I have to be able to tell you the row initial, the thing that went in. Again, as an experimentalist, a lot of times your machine is not behaving properly, or at least you haven't calibrated it, and you don't know this. I cannot do this math. I have to do the experiment the other way, which is to build a machinery that I think is measuring Z, run it a bunch of times. All I'm going to get is this bit string here, and then I'm going to infer backwards to what the state of the qubit was. The problem here is that the number of shots I do, let's call them n, the uncertainty goes as 1 over the square root of n shots. So let's imagine that like you'd like to figure out this number to an accuracy of a part per thousand. That means you have to measure the Z operator 1,000,000 times. And then, of course, the block vector has x, it has y. So for 1 qubit, 1 measurement, medium good fidelity of 1 part per thousand, that's 3 million shots of your experiment. And it gets exponentially worse. The number of things I have to measure, so this block vector, for 1 qubit has 3 components. For 2 qubits has 15 components. For I need another letter here. For q qubits together has 2 to the 2q minus 1 components. So the number of things that I measure scales exponentially in the size of the system. So as I tell it to my students in the lab, full tomography is like irksome for 1 qubit. It's really troublesome for 2 qubits, and basically don't go there for 3 or more qubits. You're not going to see full tomography of like a 10 qubit system because who has time to do the 10 billion shots? And if I'm trying to use this state of the system to tune up a pi pulse, then I also have to prepare a bunch of initial states to see the different ways the system responds. So in fact, quantum computers are like really informationally starved. They have all these quantities like x and y and z that are continuous like analog values. You get out 1 bit per shot per measurement. So figuring out the full state of your computer is just, it's not a thing you're ever going to do on a big machine. So in fact, the whole miracle of quantum computing is that we can't just figure out the state of something, but we can still build algorithms and operations that with the very limited information we can have, still do something useful. It's not automatic that this would be okay. It's kind of, again, one of the miracles. Because quantum systems are very hard to figure out because of the property of measurement. Okay, so that's my sort of general rant on measurement. I want to say one more thing here, and then we'll take a break. And after the break, we'll talk about how we actually build these machines in superconducting circuits. The one last thing here, I want to be more precise about this idea of quantum non-demolition. So let's imagine I'm going to do a chain of measurements. So I'm going to set up my Z measurement operation. I'm going to prepare some initial state. I'm now going to then take this outcome and feed it right into another measurement operator. So I'm going to get an answer M1 here. I'm going to get an answer M2 here. I'm going to get an answer M3 here. The kinds of measurements that I've built you are quantum non-demolition, which means the first one will take this state and project it to either 0 or 1, and then tell you which one it did. Will the second one do anything? No. You're already in an eigenstate of the measurement operator. If this one is 0, this one will be 0, and that one will be 0. So these Q and D measurements, which at least people have different definitions. The one I'm using is this. You can repeat it, and the other ones don't do anything different. This is very handy because my meter lives up in the classical world, lots of dirty classical noise is going to get into my meter. So, in fact, imagine that I don't get to see this pure outcome, that somebody else flips a coin and adds it on top of this answer. So this fidelity, how likely this is to tell me this state, is quite low. If my measurement is QND, and again, this is very computer science, this is how the bit flip codes work in like classical communication, I can just repeat it, and then basically majority vote the answer. If I run this system 3 times, I get 3 zeros, definitely 0. 2 zeros and a 1, I'm going to assume it's 0. And so then it'll take 2 of these answers being incorrect before I fail and I get the wrong state of the system. So as I'll show you in circuit QED, the kind of way we do the measurement inherently relies on this sort of Q and D nature of this interaction that I've built. There are other kinds of measurements. They are quite handy. This kind of, I guess it's low for you to see it. Before we had good superconducting amplifiers, this kind of measurement where you measure the qubit and blow it up in the process was the best thing that we had over in the 4th floor of Becton. Here's a paper. The person who did it was Matt Reed, so we called it the Reed out. Yeah, thank you. But this was no good. At the end of the day, you can still have this as like the last thing you do at the end of the quantum computer. If you had a measurement that was not QND, but it was like a little bit better fidelity, you'd run it at the very end to get your final answer, blow everything up, and then put it back together and move forward. Yeah.
I was going to ask, how do we have confidence if the initial probability is low?
So you're saying like this one?
Yes.
Yeah. I didn't calculate how likely it is that you get 0, 0, 0. If the initial state is 1, it'll never occur. You'll always get 1, 1, 1. So you'll notice that this machine doesn't say anything to you about, okay. Let me say it slightly. I still think this statement is the correct one. Measurements tell us very little about the past. So I'm going to give you a state in the box, and I'm going to tell you that I'll prepare it for you every time. You can measure it as many times as you want. I'll keep preparing it for you. We have to do the game like that. So let's do this. I'm going to give you the state. You're going to measure it, and you get the outcome 1, like you wanted. What's the only thing you can say with confidence about the initial distribution of that state? All you can say is it's, if I write the state like this, psi equals alpha 0 plus beta 1, from one shot, 1, 0 in this string of measurements, we can say that alpha is not 0. That's all you can say. Does that make sense? Now, if I give you 10 in a row, you're like, alpha's probably pretty close to 1. If I give you 100 in a row, you're like, alpha's really pretty close to 1. I give you 1,000,000 in a row, but you'll notice that like the individual shot just gives you like a very little piece of information about the past, but perfect knowledge moving forward. Measurement is super weird. We do it to, it works much better at preparation than the thing that we think it's designed for. I think, I don't know. Other people think that's weird. Again, I do it every day. I still think it's weird. Does it answer your question? Sorta? Okay. We're supposed to take a break. I will see you back here at, 2:30? And then we'll do the second half. Now that we've set the stage, we've set up the machinery, all the ringers in the back have left. Now we get to the actual topic of today's talk, which is how to do measurement in this system, circuit QED. So I don't know. Whoops. Oh, I reset the talk when I showed you guys my logo. I don't know how much you've heard this week about like how we actually physically build this stuff. But so we work in the field of superconducting circuits. So everything for us is superconducting metal, laying on silicon or sapphire, acting as like just an insulator to hold it up. Okay? And then we basically have 3 elements. We have capacitors, we have inductors, and we have this thing called the Josephson junction. So it has this X symbol here. You can think of this in terms of inductance as a nonlinear inductor. So you have some energy scale EJ for the junction. And then if you take this phase difference of this superconductor across it, you have EJ cos phi. So when you have a cosine, you expand it in Taylor series. You'll get phi squared as the first term. A thing that has phi squared as its first term is a linear inductor. Phi squared over 2L is the energy of the inductor. For the Josephson junction, you get phi squared, and you take this whole thing and say, that's like an inductance. So this circuit you can see here is like a parallel LC oscillator, plus some nonlinearity. The leading nonlinearity is the fourth order here, so phi to the fourth order. All that really matters for us today is that you can think of these Josephson junction circuits, particularly this one called the transmon, as a junction with a big shunting capacitance such that I'm going to get almost a harmonic oscillator. So omega q dagger q, or omega a dagger a, that's our harmonic oscillator, everyone's favorite quantum and classical system. And then this second term here, this leading order and harmonicity, what it's going to do is if you take the energy structure of the transmon, it's going to take this initial transition, which maybe is going to be 5 gigahertz, and lower the transition above it by this parameter alpha. So alpha is like 200 megahertz for us. So this would be 5, this would be 4.8, 4.6, 4.4. So all it's going to do is take a harmonic oscillator and disrupt the level spacing a little bit so that now I can zoom in and address these 0 and 1 levels because they're a different frequency transition than everything else. And I will pretend that it's a qubit. In real life, it has lots of states. Like I said, we write them either GEF or 0, 1, 2. I'll show you in readout when things go wrong. You tend to see these other states. If you're using it as a computer in a machine, typically you're hopefully only using these bottom 2 states and not trying to get out of them. This is what it looks like in the laboratory. It's like a big capacitor pad, and then tiny, so this is millimeter scale. Then tiny right here in the middle at the few hundred nanometer scale is a Josephson junction. Okay? Questions about that? So this is the physical basis of the transmon qubit. When I talk about readout today, what we're going to need to know is that there is this fourth order term here. And this is going to give us the interaction. The thing that was a C0 before that made the qubit and the flying pulse interact is going to be exactly this fourth order term right here. That's kind of the key takeaway for today. The other thing we have in superconducting circuits, like I said, is just inductors and capacitors. If you just take an inductor and a capacitor, you put them together, right, that will form a harmonic oscillator. It's like before, except it's not been perturbed. The 0 to 1, the 1 to 2 transition are all exactly the same. We can build these in the lab, describe them by like h bar omega c dagger c. We can build them in the lab as really lumped things, like this picture right here. Like this is really the inductor. Oh, sorry, the capacitor. This is really the inductor. Or we can build them as like distributed 3D transmission line or cavity-based harmonic oscillators. So these are the basic building blocks. And then what I want to do from that is to try to build up that same measurement apparatus that I told you before kind of abstractly in real life. So the most straightforward thing we could do with our transmon qubit once we have it is just connect it to an output line, connect it to the microwave world, and let that photon that's inside the qubit come out. So the simple circuit that would get you some kind of measurement, though not really the kind that we want, is to just take this transmon oscillator here and connect it to a transmission line. If I built a detector that comes here where this triangle symbol represents the microwave port, what would happen is that if I prepare some photon inside here, like the E state, it would just become a photon that leaks out into the transmission line. It's bad for 2 reasons. One is, obviously, the state is now dead. The qubit, it's leaked out. There's no left behind quantum state anymore. The circuit is now empty of photons. The second reason is if I want the measurement to be fast, I'd like to set that coupling capacitor there so that it leaks out in 100 nanoseconds. Well, that means my qubit will die. So I drew you an abstract box at the very beginning of the day. I said we need to protect the qubit. We need to give it a good T1 and a good T2. The very first piece of us using cavities and transmons together to make this circuit QED platform is to recognize that like a transmon by itself is not going to work. I need to put something in between it to kind of screen it and still be able to get information in and out without destroying my qubit. And so the way I'm going to do that, I'll write it out on the board, but I also have it graphically here, is just to take my qubit and couple it to a cavity. So I'm going to extend my circuit here and just put a harmonic oscillator right here between the qubit and the outside world. I can write the Hamiltonian of the qubit, again, as just being a perturbed harmonic oscillator, so it's omega GE. I'm going to use Q dagger Q. These are the usual raising and lowering operators, like you would write A for a harmonic oscillator typically, to keep me straight. Instead of like AB, I'm going to use Q for qubit and C for cavity. So Q dagger Q minus alpha, Q dagger, QQ over 2. This is the anharmonicity again that keeps me from being a harmonic oscillator. The cavity's Hamiltonian is just omega cavity times C dagger C. Okay? I need them to interact, so I'm going to take an interaction term. And from this coupling capacitor here, you can imagine that electric field here will couple to electric field here. So that kind of simple capacitive coupling I can write as some G QC dagger plus Q dagger C. If these two frequencies, omega cavity and omega GE, were equal to each other, if I put a photon in here, it would just slosh back and forth between the cavity and the qubit. Okay? That's not what I'm trying to do. I want the qubit photon to stay in the qubit. So I'm actually going to detune the two on purpose. So I'm going to define some term delta, the difference between the cavity and the GE transition of the transmon. If that is much greater than the exchange rate G, that is like how fast the light is sloshing back and forth between the two, they will enter into what's called a dispersive interaction. Okay? This is I know this is like, all of a sudden I'm just filling the board with math, but I'm just trying to take two simple elements, the qubit itself, the cavity. I'm going to couple them to each other just very simply with a capacitor. And now I'm going to not let them be at the same frequency. This, again, this is a much older trick than our field. This is done, with atoms and with optics all the time. The very nice thing that happens is now I can take these three terms, 1, 2, 3. I can, write them nicely for you on the board. And then with this approximation, I can write now an approximate Hamiltonian, which just gives you back the same qubit you started with. It gives you back the same cavity you started with. But now I've drawn you this interaction term here. It goes from direct exchange, which is bad. My qubit is sloshing into the cavity and not staying where I want it to stay, to this term here, chi Q dagger Q, C dagger C. And this term is sort of magic. The amplitude of chi is given by how anharmonic is a qubit. I told you this is the only anharmonicity in the system that causes fun interactions. And then G over delta is basically how hybridized the systems are. So G over delta is going to be something like 0.1. You can kind of think of it as like 10% of the electric field in the qubit resides in the cavity, and vice versa. And because they kind of overlap with each other, I get this cross-Kerr interaction, Q dagger Q, C dagger C. What does that do? Well, what that does means that they influence each other without exchanging energy. So I'm going to erase this because it's all on the board at the right. What it's going to do is take the frequency response. If I now look at the cavity, I now have to index it. So its energy is just omega C. But you see here that if I put one photon in the qubit, then Q dagger Q will be 1. And the total energy of the cavity will be omega C minus chi. So if I put the qubit in the ground state, the cavity transition frequency is here. If I put the qubit in the excited state, the qubit transition is here, shifted down by chi. And this continues. If I put the F state, the H state, every time I add a photon to the qubit, it just pushes the cavity down. It does not exchange energy. That's the key thing here. It doesn't put a photon in the cavity. It doesn't put a photon in the qubit. It just shifts the energy. And I'm going to exploit that shift to do my dispersive readout, to do the good readout that I've been trying to set us up for. Nothing in quantum mechanics works one way. So then the cavity will also split the qubit. So now if I draw the GE transition for the qubit, I now have to tell you how many photons are in the cavity. If I put one photon in the cavity or two photons in the cavity, it will shift the frequency of the qubit. this this is really cool, and I will tell you that, you know, on the Yale campus, there's like 15 years of experiments basically just taking these two mutual versions of the picture and using the qubit to control the cavity and the cavity to control the qubit. One very obvious consequence of this, let's imagine I had a way of preparing the cavity in the Fock state 1. And then I try to come and pi pulse my qubit at this frequency. If I apply a pulse whose spectral width, so a pulse whose width is smaller than chi, for instance, I'll only flip the qubit state if the cavity is in 0. If the cavity is in 1, I'll fail to flip the qubit state. It's called a conditional pi pulse. So these dispersive shifts, they're just awesome. The field of circuit QED is basically named for this trick, named, as we were discussing on the break, for the older field of cavity QED, which is then like a riff off QED. The piece that makes it special, and what we often like sort of shortcut mean by circuit QED, is this business of taking our qubit, dispersively coupling to the cavity, getting these mutual fourth order based interactions that allow them to interact with each other but not exchange energy. So now I've restored my box around the qubit. It will not be able to decay out through the cavity. And then I can interrogate the cavity, and because of these mutual interactions, learn about the state of the qubit. This is like a schematic of how they're often built in the laboratory. You'll see that this is what's called a post cavity. There is a λ/4 excitation, basically where you have no electric field at the bottom and a strong electric field right here at the top of this post. The E fields point radially outwards. I put in a chip with a transmon on it. The two E fields point the same direction. That's basically the 3D version of this kind of coupling capacitance between them. And then I'm going to put in some kind of port here called the readout port, which again is going to be equivalent to this, connecting the cavity but not the qubit to the outside world. Florian was alluding to the fact that we have a lot of artifacts in glass boxes. If you're concerned, for instance, these frequencies are kind of close together. Let's say the cavity is 7, and let's say the qubit is 6, and you really want this to be a very strong coupling. You will have the qubit decaying through the cavity. This is called the Purcell effect. In atomic physics, the Purcell effect is usually a good thing. In circuit QED, where we live, where these interactions are very, very strong, it's a bad thing. So you will put what's called, from a microwave, do we have any microwave engineers or electrical engineers in the audience? Okay. So you will then just imagine that instead of a simple coupling capacitor here, you will just put a filter to block light from leaving at the qubit frequency. It's called a Purcell filter. One of the examples in the boxes, I didn't see it over there. Is it over in Beckton?
This one is in Beckton.
Yeah. One of the things you may have walked by on your tour yesterday, this is a piece of like waveguide, like a foot long. This one's actually sort of partially my fault. It's again, it makes your qubit like the size of a Costco hot dog and bun, which got us in trouble on the scalability aspect. But you can just build these systems. You can use microwave tricks to have this beautiful, strong interaction, to have a very fast cavity that's very good at moving the pulse in and out in a hurry, and to protect your qubit. Okay? So that's the box. That's the whole, that's the interaction that I need to use to make these things work. Let me pause there for questions. Yeah.
Maybe you could explain the carbonization technique.
Oh yeah, sure. So this this exchange interaction, Q dagger C, is just a direct exchange. So again, if you put a Fock state on the left, it'll go to the right, it'll come back again. So this is just a photon exchange. If you make the frequency different, then you'll kind of choke the exchange off. So you can imagine that as I if the cavity's at a fixed frequency, and I'm going to tune the qubit through it. So when you're on resonance, when the two frequencies are the same, when omega cavity is equal to omega GE, then the two systems they will fully hybridize. So instead of like cavity and qubit, at this crossing point, you'll end up with one excitation that is half qubit, half cavity, and another excitation that's half qubit and half cavity. It's like singlets and triplets that you see in sort of classical and quantum physics when you have energy exchange between two objects. If you go over here, where they're far off resonance from each other, so where this detuning between them delta is much greater than the interaction. So this is 2G, this is how much they split on resonance. If you go over to where the energy difference is much bigger than G, then like the photon, when it's in the qubit is 5 gigahertz, when it's in the cavity it's 6. That energy difference is going to stop the qubit from just hopping back and forth. If you do perturbation theory, if you say, well, does anything happen? To first order, it doesn't exchange anymore. They just influence each other's energies a little. And so that influencing each other's energies a little will basically, if I want to get specific about it, if my old modes Q and C had these operators, the new Q, ooh, that looks like a G, sorry. The new qubit operator, Q twiddle, is going to be the old qubit operator plus a little bit of the cavity operator. If I take this term I had before, alpha, A dagger, Q dagger, Q dagger, Q, Q, and I plug this in, I will get two terms. One is going to be Q dagger, Q, C dagger, C, and it's going to have an amplitude G over delta squared alpha. So that's exactly that cross-square term I've shown you before. You will also infect the cavity with a little bit of the anharmonicity of the qubit, so you'll also get a term like G over delta to the 4th power C dagger, CC. So what I'm doing by this sort of not quite putting them on resonance but still coupling them to each other is, like I said, to sort of infect the cavity with a little bit of the anharmonicity of the qubit, but not allow them to exchange photons. And so I'll get this shift, which conserves the energy of each system. And technically, this is not a good thing. This is kind of a bad thing that gives people problems. But you'll notice that if G over delta is a small number, this is G over delta squared smaller than this. For readout cavities, it's not a big deal. For very high Q cavities, like in Rob Scholko's laboratory, this is not so harmless. Long answer to your question. Did I get at it? Other questions? Okay. When I now have built this system, so the qubit, the natural states of the qubit are Fock states: 0 photon, 1 photon, 2 photon. Cavity, you can kind of look at it two ways. One of the sort of more quantum ways to look at your cavity is to say you can also have some superposition of 0 and 1 and 2 and 3 and 4 Fock states in it. By clever pulse engineering, not just this static drive here, but if I apply fancy pulses, I could actually build a version of this system where, for instance, I prepare the qubit in alpha G plus beta E. And then I could prepare this system in, for instance, the ground state. I could build that C naught exactly like I showed you before. And so what I could do is build a version of the measurement apparatus where if the qubit's in E, I will put 1 photon in this cavity. If the qubit's in G, I will put 0 photons in this cavity. That then, photon or not, will leak out. And my detector could be some Fock state detector. It goes click if it sees a photon. It doesn't click otherwise. I could do this just like sort of real atomic systems do. It's in some sense very natural. It looks more sort of quantum when we use Fock states in the cavity. It turns out to be a bad idea in practice because I have to build all sorts of microwave machinery here. I need filters and cables and circulators and amplifiers and all sorts of stuff between me and my detector. And the problem with the Fock state is if it goes through this and it dies, I just don't get a signal. So although this is maybe a very natural way to think about the system, really Fock states 0 and 1, sort of practicality is going to make us do something that at first just seems like, I don't know. Like you're going to say, Michael, why are you now going to write 4 boards of math? And the reason why is it's going to work better, but I have to sort of get there. if I take the classical oscillator, okay, purely classical, no quantum mechanics, I don't have any idea of a photon in the system, and I capacitively couple it to the outside world, and I drive it with an oscillating field with some amplitude at cos omega dt, okay? Purely classical. It's like a kid on a swing, except instead of position and momentum, it's electric field in phase and quadrature phase. What will happen to this system? If I turn on this drive at time 0 and it's resonant with the harmonic oscillator, what will happen? It's going to build up. And in the IQ phase, so I can say that whatever oscillating voltage builds up inside this perfectly classical harmonic oscillator is going to have some amplitude A prime and some phase phi prime relative to the drive. And I can define it in terms of I, which is it oscillating like a cosine you can think of? Or Q, is it oscillating like sine? In the picture of classical and quantum harmonic oscillators, these same in-phase and quadrature phase components are often noted as X and P to make it look like a spring mass harmonic oscillator. Okay? This amplitude of a field is purely classical. Like you said, if I apply the drive as a function of time, so I turn it on for some period of time, then I turn it off. The the I and the Q as a function of time will ring up, then it'll ring down. Some other shape. Okay? This is sort of representing the steady state where it is after the drive's been on for a long time. In reality, if I draw you in the IQ plane, what's going to happen? It'll take some kind of trajectory. It'll ring up. It'll ring back down again. So, I know we have computer scientists in the room. Are you aware of something like this being used in sort of our modern cell phones, our modern Wi-Fi?
I use this module.
Okay. So, but also like your cell phone is using it right now.
Probably I'm not sure.
So this is a very nice classical communication technique. You basically have a classical oscillator. And if I take you my IQ space, let's imagine I want to send you 2 bits of information. What I would do is drive the oscillator with this phase if I want to send you the bit string 0, 0. And this phase if I want to send you 1, 1. And this one is 0, 1. This one is 1, 0. It's kind of nice because I always send you a signal. You don't have to worry about like something versus nothing. And even if I add like classical noise, because I'm too far from the base station or because my body is absorbing the radiation or whatever, as long as these Gaussian distributions, so like they're really Gaussian in terms of my scribbling here, as long as these centers are well separated compared to the standard deviations of these Gaussian distributions, then this is a perfectly nice way of sending information purely classically between one person and another. Every time I talk about this, I'm not a computer science expert. I think that's hopefully clear by now. I want to make sure I'm not messing with you guys, so I do what everybody does and I read the Wikipedia. This is quadrature phase shift key QPSK. Okay? It is a perfectly good classical way. It doesn't use Fock states like the measurement machinery I built you before. It doesn't use qubits where it's like 0 and 1. It uses these Gaussian states. It uses coherent states to send to send signals back and forth. What I'm going to do in circuit QED is take this machinery right here and take this classical communication idea and use it to measure my qubit. So you can imagine that instead of these multiple states here that are separated in IQ space telling me about these classical bits, I want them to tell me the quantum state of this qubit. Let me pause for questions there. Yeah.
What would be the role of transmon if we can make it better, like better transmon? What would be the role of transmon?
Okay, fine. You're asking where, okay. This system right here does nothing because the transmon I'm just measuring it. I'm preparing a transmon, I'm measuring it. In a I'll show you a picture of Google's processor towards the end of the day. This is like the readout setup. This qubit is going to be talking to a bunch of other qubits. They're going to form the quantum register in a quantum computer. And then each one of them is going to have one of these readout resonators strapped onto it to allow the readout channel. This right now is not a quantum computer. It's just a little physics experiment where I'm just trying to build up for you readout. Then I got to couple the qubit to a bunch of other qubits to build a quantum computer. Is that? Yeah. Okay. When you go to IBM or you go to Google and you look at their website, they have like little dots with lines. The lines are like connections between qubits. Every one of those dots is one of these readout one of these transmons. It has associated one of these readout channels. Okay. All of this stuff I can draw for you here applies quantum mechanically to a quantum oscillator that I'm driving, except I think most people will remember like the Heisenberg uncertainty principle, that the quadratures x and p don't commute. So we learn in our basic quantum that x and p don't commute, and therefore what we say is you can't know x and p to arbitrary precision simultaneously. Another way of saying that is that instead of being like classically, this width, the Gaussian distribution at the end of this lollipop here, could be as narrow as I want. Quantum mechanically, there is a minimum width here because of these quantum fluctuations. And therefore, when I start to talk about how hard I'm going to have to read out the qubit, how much light I'm going to have to put in this cavity to figure out the state of the qubit, there's now a natural meter stick that I have to be bigger than. If I want to tell this apart from this, then if I redraw these as like Gaussians, if this is sigma, this is the quantum fluctuations, and this is the separation, I need the separation over sigma to be big. Yeah? I cannot read out with a small number of photons without having the two distributions overlapping each other. And if they overlap each other, it's either a bad projective readout or a fun quantum experiment, depending on the day. But it's not like the right way to do readout for your quantum computer. So quantum mechanically, these coherent states are a little bit irksome. They're very much the classical sort of trajectory. In fact, they have what's called the correspondence principle. These trajectories where the center are is exactly the answer you'd get from classical mechanics. But the width, the quantum fluctuations, are the unique feature of the fact that they're in a quantum system. Formally speaking, I tend to write them, well, not, one tends to write them with the symbol alpha. So I will take the system, it has a center, this is the real part of alpha, this is the imaginary part of alpha, it has the quantum fluctuations. I will describe this state alpha as a ket, and it has this strange mathematical property that, how do I define this ket? It is the one where when I act a lowering operator on it, I try to pull out a photon. So A acting on alpha is actually an eigenstate. This is like my least favorite part about coherent states in this measurement journey we're on. Coherent states are just a little bit funny. They're a lot less intuitive than like Fock states. The state is actually a little bit complicated. If I try to ask how many photons are inside this, I can't. The coherent state is the state where when you pull out a photon, nothing happens. Very strange. Don't ask what happens when you add a photon. It's not good. In the Fock basis, it's like everything. It's an exponential. It's a sum over every single possible Fock state. It's got square roots. It's got factorials. Okay? It's a very complicated state in the Fock picture. I can ask the average number of photons it has in bar, and that's just mod alpha squared. Okay? It's fine. If you live with coherent states for a while, you get used to their strange properties. For now, if you were just sort of think classically, I'm like pushing a kid on a swing, right? I have a 5-year-old. I do this all the time. They're going to oscillate with some amplitude and phase. I can describe it classically. The only quantum thing here that's really going to matter for me is that there's some noise and some rules to how I observe these states. So just hang with me on it's a pretty classical state just with a few details. And the way this is going to work now is if I take the cavity, I drive this coherent state into the cavity. While it is inside, they will interact, right? But I told you that now the frequency of the cavity is a function of the number of states in the qubit and vice versa. If I now carefully draw for you the reflection response of this resonator as a function of frequency, here's this FCG, the cavity frequency when the qubit's in the ground state. Here's FCE, the frequency of the cavity when the qubit's in the excited state. They are separated by chi. These resonators have a width kappa. If I drive right here in the middle, what you will notice is that the reflected phase of the light is a function of whether the qubit is in ground or excited. So if I build my measurement machinery, if I prepare the qubit in alpha G plus beta E, if I inject this coherent state, oh, yeah, sorry. Let's call this CGG and CEE. If I have this state that I'm going to measure in the qubit, I inject this state alpha into the cavity. Again, what's going to happen, right, is that the phase of that state is going to flip in IQ space. So let's imagine that this shift in phase is pi. Then what's going to come out is, again, a Bell state. So this is psi initial. The psi after the interaction is going to be CGG alpha plus CEE minus alpha. I have flipped the state of this coherent state by pi. In IQ space, if I return to these drawings, just like this QPSK idea, I'm going to have this state plus alpha flying out down the transmission line towards me if the qubit's in G, minus alpha if the qubit's in E. And so as long as these two states can be readily discriminated, then you can kind of think of this as a funny qubit. Like the state 0 is plus alpha, the state 1 is minus alpha. They are technically speaking Gaussians, right? If I were to draw the overlap along I, formally speaking, the Gaussians have to be infinitely separated before there is no overlap between them. They're always going to have, no matter where I draw my cut line, some kind of probability on the wrong state of this decision that I want to make. But they fall exponentially. So as long as they're separated by several times their width, we can round it off and say that these two states, I can write formally mathematically that minus alpha and alpha have approximately 0 overlap. Okay? So at the cost of invoking these somewhat more mathematically complicated coherent states, I build a nice quantum readout for my system that behaves just like the handy-dandy, Wi-Fi readout that I want to use. And I can have all the machinery and all the fun stuff that I showed you before, and it's all going to work great. Let me pause for questions. That's like this is this is like mathematically the worst and grossest spot of the lecture. Once we get past this, we're basically home free. So let's pause here for questions again. Okay. So one of the things we do in my laboratory as pretty much an ongoing business for the last more than a decade is we try to build these systems. And again, quantum mechanics only sneaks in here through this uncertainty relationship. If you start with a coherent state, what I've told you before is that this width here of the initial coherent state is non-negotiable. It's half in photon units. If I want to build a quantum processor, something that will then make it so I can read out these states, it turns out that if I want to see this full IQ picture, I have to add another half. So in photon units, this width is going to be 1. So my separation needs to be several times 1 to get a good readout. And of course, on top of it, I've got technical noise that's going to add on top of that as well. And so if I do a readout, basically all we really need to do is to read out with enough photons and a low enough noise. I really want to get to what's called the quantum limit, where this noise is as little as I can get away with. And this is something we can pretty much do these days in the laboratory. And then I'll get a nice, strong projective readout. What I don't want to have happen is this. So in terms of colors here, this is the quantum noise that's unavoidable. This is the unavoidable added noise of the quantum amplifier. The rest of this is the technical, the classical, the sort of just troublesome noise that adds on top. What I don't want to do is have that noise dominate the system. Yeah.
And you control that, I guess, the overlap using frequency?
Yeah, I controlled, yeah, okay, good question. So just like when I push my kid on the swing, how hard, how much I displace, how much voltage I have here away from the origin is how hard I'm driving the resonator. So exactly like you're saying, if I want them twice as far apart, I just drive them twice as hard. It turns out, I'll show you a picture in a few slides, really bad things happen in real life when you do this, but that's the idea. I want to build an again, it's not the topic of today's talk. I want to build a quantum limited amplifier that works really well. You can get one from my group, you know, like they're real things. They're sitting over there in the glass box. You can tell we can do it in a while because it's sitting over there looking kind of dusty. I want to just drive hard. I want to get a good separation, and then I'll get a beautiful readout. That's the idea. Here's what it looks like in real life. Oops. Oh, good. Here's what it looks like in real life. So here's an example. So I think we had fun discussing earlier how I can use measurement for reset. This is a real experiment from my laboratory when I was a postdoc. It's exactly what you see here. We're going to first measure the qubit. We're going to take the outcome here, the answer. Sorry. It looks like this. So this blob is exactly the Gaussian blob I've been trying to draw you for the qubit being in the ground state. This is the Gaussian blob I've been trying to show you for the qubit in the excited state. Here's the Gaussian blob. It turns out sometimes the qubit is in higher states. I showed you it has many levels in the transmon. We just kind of pretend this doesn't exist. Sometimes it's in the F state. This happens very infrequently. This is not a linear histogram. This is a log scale histogram, okay? So yellow means that it is 10,000 times more possible, like it happens 10,000 times more often than black. So these red events are occurring like less than 1% of the time. And so what I can do here is prepare the qubits in the ground state. I always want it to be here, either in the excited state or the ground state. If I read it out in the ground state, so I land on the left of this white dashed line, great, do nothing. If I land on the right, I apply a pi pulse that will flip it to the excited state. If I then do that, and then do a measurement and this dreaded tomography stuff at the end to show you what I did, then you'll get these two distributions right here. And you see that what I want is that when I want to have the ground state, only this blob occurs. When I want to have the excited state, only this blob occurs. And if nothing else was here, this would be like 100% fidelity readout. So this is circa 2013. It's not perfect, but it's pretty good. So the fidelity of this process is like 2 9s and a 4. Of the 6 times in 1,000 it goes wrong, 1 or 2 of those times is the fact that the qubit's relaxing. So when I prepare the excited state, you see these like streaks. Those are quantum jumps that I caught mid-flight. So a couple times per 1,000 it relaxes. This pi pulse here is part of my sequence. If it's not accurate at the part per 1,000 level, it'll tend to like over or under rotate. So I won't get exactly the excited state. I'll get some more ground counts. That's about a few parts per 1,000. And then what's called assignment fidelity is, again, the idea that this Gaussian and that Gaussian don't perfectly, they're not perfectly distinct because they're not infinitely far apart, is like 3 parts per 1,000. Okay? And this is 12 years ago now. And so coming back to your question, which was exactly the right one, how do I make it better? I should just drive harder, right? At this time, the amplifier we were using couldn't handle the pulses. Because, see, things are a little bit problematic when I try to do engineering. When I try to write the separation divided by sigma for the system in quantum units, eta is basically a measure of how quantum efficient your amplifier. N bar is like how hard you're driving. Kappa is how fast light enters and leaves the system. And Tm is your measurement time. The problem is the qubit's trying to die exponentially while you're trying to read it out. if you would like to have 1 part per thousand of decay, you need to read out in 1/1000th of the T1. So even if the qubit lives a millisecond, you have to be fast compared to a microsecond. And that's pretty tough. And so on this graph here, what I've shown you is this idea of like just push harder, which is very like where we wanted to go. Means you make the amplifier so that you can like tolerate these very tight pulses. Then let's just pulse shorter. The best readout is to take the simple system and do like a 1 nanosecond pulse with like the world's scariest power. Just drive thousands of photons into the resonator. And then if the qubit didn't have T1, and if the cavity had infinitely fast response, you would see that it's not that hard. Here's 1 9, 2 9, 3 9, 4 9s, 5 9s, 6 9s. Like, it would be very handy. This is why your cell phone works. Just averaging slightly longer, they suppress the errors because their states are stationary. Qubits, unfortunately, decay. So I've started to put in details of the experiment, like the fact that the cavity has a finite lifetime. That means when I do a very sharp pulse, to get lots of photons in, I have to start driving crazy hard. And so then what I have to have is a competition. This is like the bandwidth of the system given by the bandwidth of the amplifier and the cavity. I need to push it down in time, which is so wide in frequency. And I need to push it up in power. Okay? So the 2013 amplifiers were kind of down here at the bottom right corner. And I have to make life even worse one more time. I have to put that qubit exponential decay in. And see, what that's going to do is going to kind of give you these like cliffs here. So basically, this is 1% of T1. That's 99% decay. This is 1,000th of T1. That's 99.9. So now you see that I'm pushed really up into this corner of space. Okay? All very practical sort of microwave engineering that I'm just fighting. And so to sort of make a very short story of 12 years of my life, so this is a new paper. It's just been out in the archive for about a year, and now it's going to appear something like next week in print. Here are the same kind of pictures I showed you from 2013. Okay? They're, again, log scale histograms. Ground state prepared beautifully, a little bit of excited state contamination. Excited state prepared beautifully with a little bit more G and F contamination. And then I built an amplifier that would tolerate all the power and all the bandwidth that I needed. And so I just pushed it up and up. And yeah, actually, that's awesome. I saw many brows furrow. And you said, like, what on earth is this? And yeah, that's a very good question. So this is kind of where we are now. In the lab, in the world, Google makes these things. You can buy them on the internet from like Quantum Microwave. The amplifiers have become sort of well-behaved. The actual transmon circuit QED, all the Hamiltonians I wrote for you on the board over here, you'll notice that they were all sort of approximate. We had been sweeping lots of details under the rug. As you can read in these, ooh, they're kind of small, but as you can read in a whole bunch of recent theory and experiments from groups like Michel Devereux, from theory groups like Alexandre Blay, the Hamiltonian of our system, when you push it too hard, tends to explode. So these other sort of, you see these, like each one of these yellow states? That's an almost stationary state of the qubit. But this one might be 22 photons in the qubit. And this one might be like 11 photons in the qubit. And this one might be 3 photons in the qubit. So what's happening is it's exploding out of the space. And so, unfortunately, you know, for like Nathan has come back in, Nathan's dreams, we need to have 4 and 5 nines readout fidelity. Where we've gotten to in the lab to sort of bring it here at the end of our 2 hours to sort of close to an experimental space is that this simple picture we showed you works. It works really well until about 3 nines, so 1 part per thousand. To push it past that requires some sort of massive re-engineering of the very fine details of the Hamiltonians of the systems that we're building. Yeah?
So some qubits are able to handle more photons than others?
Yes, and we are in the process of trying to turn like that intuition into like an engineering project. So for instance, well, I'll go ahead and show you the slide early. So in Michel's group, student Pavel Krylovich, who just graduated, he looked at the physics of the system. And so typically, like, we would use a qubit here at 5 and a cavity here at 7. He determined, you know, his group determined that if he pushed the qubit very far down in frequency and the cavity up, it was more favorable. So he tacked on like another 9 of readout before he hit another limitation. And so you can imagine that we all have to sort of do things like this. We either need to figure out tweaks to our Hamiltonian so that we can drive it as brutally hard as we want without breaking something. Or you could imagine looking at a different kind of qubit. You could look at a fluxonium. You could look at, I don't know, a Kerr cat or something else and try to find if changing the underlying physics will help. It doesn't seem that it's going to be easy, whatever qubit you choose, because like the problem is that the Josephson junction is kind of too nonlinear, and all of our superconducting qubits involve Josephson junctions in one form or another. Yeah.
So was there a noticeable trend with lower frequency qubits in the experiment that you brought up?
Yeah, in this paper, he got like almost an extra 9.
So was it even in your paper when you did your research?
Oh, I don't use 5. So he had to really work hard to push the qubit down to 900 megahertz. All the qubits in my laboratory are 5 times higher, like 5 gigahertz, 4 gigahertz.
And there's no constant value that you kind of vary?
Okay, so that's not today's talk, but like here, if I just show you here, this is a picture, I'll come to this in a bit, but this is a picture of Google's quantum processor. And so every one of these circle things is a qubit. And so when you put a bunch of qubits together into like into a 2D grid, they can't all have the same frequency because then you can't like individually control them, right? So you have to pick which frequencies you're going to tile them out. And so you end up saying like qubits all have to fit in this frequency band. And the readouts have to fit in this frequency band. And the drives fit in that frequency band. And so you end up like apportioning all of your frequency space, and you kind of back yourself into a corner. You have certain assumptions that are not very easy to undo. This readout works really beautifully. It is, again, this like 1 qubit system that's not a computer yet. You know, you can imagine that then if this is what you want to do to make your readout better, you now have to go back to this and rethink all your frequencies, because now all your qubits will be 5 times lower in frequency. Everything will get all smooshed around. That is an interesting separate research on like how you build like modular or non-modular quantum computers. You push, well, here, yeah. I mean, so for instance, fluxonium naturally likes to be at low frequencies. So people have been building ideas for fluxonium processors, and they've been exploring this space. So it's not that we have no way forward. I showed you a bunch of, I know the font was small, but I showed you many experiments and many theory results. Now that we kind of know, this is where we look for this problem. When you drive too hard, here's ways to explain why it's going so horribly, horribly wrong. Then like, that's an awesome design tool. It goes in your pocket, you use it. But when you rip out, you know, you're building a big complex machine, you rip out one of your fundamental assumptions, you kind of have to like rethink everything. So you can imagine that if like you were to look in the press over the next year, maybe you will see that all of a sudden, you know, IBM says, retile it's in 10 times better. It might be from them taking these kind of ideas and figuring them out how to shove them into their processor. Other questions? Yeah.
So, like when you look at this abstractly, when you define on the previous slide, you define like your measurement arrows as
Yeah.
basically preparing some state and measuring it, right? But like kind of, you know, on a level of abstract operators, you will run into kind of consistency problems when you try to, you know, do a state tomography and measurement tomography.
Yep.
So like, how do you guys deal with that, or like what's the?
So, okay, there's several questions here. One is you're asking, like, how do I do tomography to prove that it's this good?
That's right. Like you kind of have to always assume something, right? Like for example, in the slide on the right, you say that you prepare to G. So how do you know that?
Yeah, okay. So because measurement is how I learn about the systems, I'm basically going to fall back on these kind of histograms right here. So, you know, in a system where it's well behaved, I can identify the centroids and say, like, these counts are F, these are E, these are G. If I want to prove to you that my readout works at 3 nines, I should be able to prepare the ground state and prepare the excited state and show you that, like, for instance, you know, if I draw a separation, what's called a separatrix, like a decision boundary here. If stuff on the wrong side of the boundary is no more than a part per thousand, then I can prove to you that I can then show you a graph, and you can make decisions on the graph to that level of confidence.
Okay, but like, wouldn't this work also if your measurement operator was something completely different?
So from a formal basis, if these shapes are not Gaussian, if they were weird,
Yeah.
if that, like, I don't know, they look like bananas, you'll actually notice that this amplifier is really good. You see how these Gaussians are really brown, really round? Actually, you were seeing my amplifier struggle in the old data. That's not an isotropic Gaussian. It's okay that it's a little bit squeezed as long as it stays on its side of the line. So how we do characterization of the readout, you know, some of it's like this. Some of it will be this idea. So if you look in papers, you will also see that people repeat the measurement many times and look at the correlation between the two measurements. So it's going to be some sequence of like, look at the histogram and do many versions of the histogram to make sure that like when you prepare known input states, what comes out matches to some level of confidence. That we can do. And yeah, I think there's 10 million experiments in these histograms. It's not, everything is irksome, I think, I hopefully convinced you today that everything's irksome when it comes to getting information out of a quantum computer. Things that keep me up at night are not actually, can I make a picture like this? It's when I come back 12 hours later, we'll have some temperature change in the system and rotated it by 10 degrees. So it's not so much like, can I do a snapshot of like this and tune it up briefly? That we can make work, or we can know that it doesn't work very quickly. The thing on top of it, like when you run a real quantum computer for long periods of time, is that you have to also stabilize them at the part in 10 to the 4 level for a day. I don't know exactly how it works on IBM machines now, but like a couple years ago, I saw some stuff from them where they like have to calibrate the machine 4 times a day. That's telling you that like that's how long they can keep such numbers stable before it's better to stop and recalibrate because something will have drifted off. We do a lot of stuff in the laboratory about basic things like if we build our experiment wrong, this rotation angle will tell you the temperature of the room. So we're like, oh, 72, 71, 70. So you build like a really expensive thermometer. And then you go end up and basically trying to crush this sensitivity, trying to like protect the system by cooling or by stabilization of temperature or some other mechanism so that you remove the susceptibility to the environment. And those parts tend to be more vexing than these kind of shots. I don't know if that answered your question.
Partially, definitely. Yeah. I have a follow-up question,
Hmm?
if I may.
Sure.
So, like, the way that you're describing readout errors now is kind of like basically, again, you prepare G and whether you measured E, right? So, kind of on the abstract operator level, this would be somehow, well, it's kind of like a classical error, right?
Yeah.
Like this like an assignment error. But like, you know, in principle, you could have some type of coherence in this measurement operators. This would be like basically off-diagonal terms if you write it down. So like, is there any
Well, okay, so,
physical reason to
well, if you, I think, I think I agree with you, and that's kind of what we were trying to get at here by trying to break to, like, I know it's kind of hard to see, but like we have what's called an assignment fidelity, which is just the separation of the Gaussians. We have corruption due to decay, and we have, I didn't actually prepare the state right because my coherent controls are wrong. So as an amplifier person, like the rotation part is somebody else's problem. The T1 part is linking to this, so the T1 part is linking to this idea of unwanted transitions of non-QED-ness. So that the thing I drew before you about QED, you measure ground, you'll measure ground again. If you measure ground in the process, you jump it up to the 21st state, you're not going to measure ground the next time. So this is the one that's most vexing right now, is that the very intense pulses we're trying to apply to the system are not QED to the extent that we need them to be. And again, when you ask for 4 nines readout, you can make one mistake every 10,000 times. You study quantum computing, you think a lot about statistics just in your everyday life. I'm not sure I can walk down the stairs 10,000 times in a row without falling. I don't know. It's a very high level of precision. You know what I'm saying? So we're just asking an awful lot of the systems. And I think 4 nines readout is not really, one would like a little bit more, I think. What do you think? 4 nines, you'd be okay, or you'd really want 5?
I think it depends on the code. But yeah, I think 4 nines is probably good enough for me.
Okay. So all we got is, we got to just lock down 1 or 2 more nines, and then we can take a break. Okay. That answer your question?
Yeah, well, again, partially, definitely.
Well,
Similar.
at some point, you just come, spend 5-6 years in the lab, and then you can get into the really get into the suffering at first hand. Okay, so then my last piece here, I think we're running a little bit short on time, but I want to come back to this magic of quantum measurement and sort of measurement being really the sort of a lot of the secret sauce, but behind error correction. So first, just to show you that measurement is still a problem. So this is this recent beyond break-even result from Google. In terms of fidelities, these are the 1-qubit gates, the 2-qubit gates, and the measurements. You will notice that the measurements are still some of the worst operations in the system. So this is bad. In some sense, you would like them to be among the best. In terms of where we're going for our more nines of readout fidelity, we've talked to you about re-engineering fundamentally, like the qubit and the cavity and maybe even their interaction. I guess this is mostly just working on the qubit cavity sort of energy scales. Things have to be very fast. And so, for instance, this is a readout from the Nakamura group that was something like 50 nanoseconds, something like 10 times faster than the readouts I've been showing you. And then the amplifiers themselves are also sort of a really important piece. They kind of need to be commodity items. The transmons with really long lifetimes need to be commodity items. Like 1 millisecond transmon is a recent paper from Princeton. Awesome. We need them to be like that every day, right? If they slip to 100 microseconds, still pretty good. We lose factor of 10 on all our fidelities. So that's kind of sort of the challenges in the field, is building both these individual components and then learning how to scale them up into bigger machines to push these numbers further down.
What is DEX on that chart?
Detection. So I think detection is built up of many measurements. Okay. So then the last thing in terms of measurement and what's magical about it, we talked about measurement operators, and honestly, the only one I showed you today was really the Z measurement operator. If you ask like what's going on for me in error correction, instead of talking about a qubit, I'm going to talk about a register of qubits. And instead of talking about a measurement operator with like 2 outcomes, I'm going to just talk about a bigger one, right? So I've got some initial state psi. I prepare a bunch of ancillas in known states. I want to encode the whole system, right? Where this awesome thing about measurement pushing back on systems, pushing indeterminate states into determinate states, is if you think about sort of what comes next as just a big fancy measurement operator. If I have a state psi no error, and I have a state psi error type 1, psi error type 2, psi error type 3, what's really going on with like the next part, the sort of the check part of the error correction codes you guys have seen, is that we're just trying to build a measurement operator whose projectors are exactly the list of states we would try to distinguish. So if you go back to the early minutes of the lecture, you would saw I took a qubit that could be probabilistically in ground or excited. If you go back and rewrite that initial thing as, I could have an error correcting code in the state of no error, or probabilistically in the state of error type 2 with type probability 2, 3, 4. What measurement does for us, this kind of quantum measurement we've described today, is kind of take a continuous error and force it in that particular instance of the experiment to resolve as either like, yes, you definitely had error type 2, now move forward and fix it, or no, you had error type 1, or you had no error type at all. This business of projective measurement, how it takes uncertain states and pushes them in a single shot onto certain states, is exactly the thing that we're exploiting all over these error correction codes. Now, there are wrinkles and complications, right? There are path engineering codes. There are lots of different elaborations. But somewhere hidden inside them is you dumping information into the environment in such a way that you force it to have this behavior. And none of this comes from sort of the unitary part of the system. It doesn't come from the gates. It comes from this unique feature of quantum measurement. So if you ask me like what's really cool about measurement, why do I really love trying to use it for these error-corrected experiments, I don't want to like spend our last few minutes together tangling us up into a bunch of math. But whenever you look at these sequences, you'll notice like there's some readout on Scylla, they're building a whole bunch of C-knots, they're talking about some check that they want to do. They're just trying to build a measurement operation that kind of cheats. If you didn't measure, your system would be a mess. But if you do measure, you force the error to either occur or not occur in that shot of the experiment, and then you just fix it. And I actually think this is awesome, and I love to pieces the fact that like we can use quantum mechanics as sort of this tool to dig ourselves out of this hole and make these machines, which really want to die, have a chance at existing as practical things in the laboratory.